In this lesson, we are going to learn to distinguish among the different types of intermolecular forces, how to identify those types of intermolecular forces in a molecule, and how properties are affected by those forces. Intermolecular forces, which can be abbreviated IMF, are interactions that occur between molecules. So bonds occur within molecules, and these are interactions that occur between molecules. And they are the result of charges, partial charges, or temporary charges in a molecule, and they are generally weaker than any bonding forces. We are going to look at several types of intermolecular forces. The first three are going to be the most important, and they will be what we see in most of our molecules that we look at in this class. We're going to start with dispersion forces, which are also called London dispersion forces, then dipole-dipole forces, hydrogen bonding, which we will learn is a very bad name for that force, ion dipole forces, and ionic forces. These are given in order of strength, with dispersion forces being among the weakest of intermolecular forces, and ionic forces, which we also know as ionic bonds, some of the strongest. This comparison of strength applies when we are looking at molecules of similar size. Let's look at dispersion forces first. We see that these are found in all molecules, and they are the result of having electrons in atoms. As electrons are moving around within an atom, occasionally they will be unevenly distributed throughout the atom or throughout the molecule and create a temporary uneven distribution. This temporary uneven distribution leaves a very small positive and a very small negative charge on the atom or molecule, resulting in the dispersion force. Dipole-dipole forces occur between two or more polar molecules. These can be two of the same molecule or two different polar molecules. They are very weak attractions, and they result because of the partial positive and partial negative that result in a polar molecule. The next force is hydrogen bonding, and this name is not a good fit at all. It involves more than hydrogens, and they aren't really bonds, they're attractive forces. However, the name was used, so now we're stuck with it. And hydrogen bonding has a very specific definition. It's when you have a hydrogen attached to a fluorine, oxygen, or nitrogen, and it's attracted to the fluorine, oxygen, or nitrogen of another molecule. The other molecule can be another molecule of the same kind or of a different substance. The name for ion dipole forces gives us a clue of what is involved. We see ion and dipole means polar compound. So when we have both an ion and a polar compound, we can have ion dipole forces. We have to have both things present. An example might be an ion such as sodium plus or Cl minus, which both explicitly show a charge. If there's no charge shown, it's not an ion. And a polar molecule such as water. You must have both present in order to have ion dipole forces. A pure substance, such as CH4 or water, cannot alone have ion dipole forces. The last are ionic forces. These occur from cations and anions. We have a transfer of electrons, which creates a positive and negative charge, and we're going to see the attraction there. We typically call these ionic bonds. Now let's look at some examples so we can better understand these forces and how we determine what types of forces a particular substance has. We've already looked at this molecule CO2 and found that it is a non-polar molecule. As a result, we see that it has dispersion forces, but because it is nonpolar, it will not have dipole-dipole forces. It does not meet the definition of hydrogen bonding. There are no ions present, so we will not have ion dipole forces or ionic forces. And this is typical of nonpolar molecules. We will see only dispersion forces. Next, we'll look at HCN, which we previously established as being a polar molecule. It will have dispersion forces because all molecules have atoms and all atoms have electrons. Therefore, all substances will have dispersion forces. It is a polar molecule, so it will also have dipole-dipole forces. It does have a hydrogen, but it does not meet the definition of hydrogen bonding because we need a hydrogen attached to a fluorine, oxygen, or nitrogen. Although there is a nitrogen in this molecule and a hydrogen, they are not bonded to one another, so it does not meet the definition of hydrogen bonding. Nor are there any ions, so no ion dipole or ionic forces. Our next example is BCl3, which we've determined was a non-polar molecule. Because it is a nonpolar molecule, we will only see dispersion forces. CH3Cl is a polar molecule. Like every other molecule, it will have dispersion forces. As a polar molecule, it will have dipole-dipole forces. There are hydrogens in the molecule, but it does not meet the definition of being attached to an F, O, or N, so no hydrogen bonding. No ions, so no ion dipole forces or ionic forces. Next, we'll look at NH3. This is a polar molecule, so we will have dispersion forces and dipole-dipole forces. When we look at our definition of hydrogen bonding, we need a hydrogen attached to a fluorine, oxygen, or nitrogen and attracted to the fluorine, oxygen, or nitrogen on another molecule. Whenever we have a sample of a substance, we always know that there are multiple molecules of that same substance present. As a result, we meet the definition of hydrogen bonding for NH3. No ions, so no ion dipole or ionic forces.